We should be able to get a bunch of it done today, if I recall. But we are introducing 3 new sets of identities, okay? These are not my most favorite identities, okay? They just, I don't know. They just aren't. They're a little, I don't know, sometimes more different. Sometimes, double angle identities I like. Power reducing half angle just are a little bit more difficult to use sometimes, but they have their, pieces that are helpful. Is it half angle, I think, that sometimes comes up, or power reducing, that sometimes will randomly come up in calculus. So, but okay, double angle identities. This first batch are called double angle identities because if you look at the variable here, it is 2u. Okay, or that could be an x, or that could be a theta, or whatever variable you guys prefer. I know you guys prefer x. But double angle identities are double angle because there's a 2 in with the variable. And so they give us a way to find the sine, cosine, and tangent of 2u using just regular sine, cosine, and tangent. Okay? Power reducing identities, notice they all have a squared in them. And the idea is a power reducing identity gives us another way to write it where we don't have any powers above 1. Okay, it does change you to double angles, so 2u's, but it gets rid of the squares. Takes you to all powers of 1, nothing higher. And then we have the half angle identities. These are half angle identities because, it's not double, it's half. It's u over 2 in each of those cases. And again, it gives us a way to rewrite them just using regular sine and cosine of the angle. Okay? You will notice a couple plus or minus there. It's plus or minus because you're basically going to have to look at what quadrant is it in and decide on the sign, whether it's positive or negative yourself. Okay? Let's see. I will say, I guess I didn't point out double angle identities. Did you catch cosine of 2u?
Yeah, that's a mess.
Okay, it's a mess. What it is, there's 3 different options.
Oh.
They all 3 work. Depending on your scenario, you pick one. Okay? But they all 3 work. Okay? Let's see. I've written in my notes that there's 2 others of this one listed in the book of tangent u over 2, but I just have the basic one listed. So, okay, let's look at example 1. If sine of theta is equal to 4/5 and cosine of theta is less than 0, this is a 3-part problem because we're being asked to find sine of 2 theta, cosine of 2 theta, and tangent of 2 theta. Well, in my brain it's obvious. I don't know, is it obvious to you guys? What are we going to be using to find sine, cosine, and tangent of 2 theta? Now? Double angle identities? We're going to be using the double angle identities because in order to find sine of 2 theta, we have to look at, okay, what's sine of 2u? What is that equivalent to? Okay, so this, because it's asking us for the 2 theta in there, this is their way of asking us to practice using the double angle. Okay, now, as you start looking down at sine of 2 theta, cosine of 2 theta, and tangent of 2 theta, and if I backtrack to the top of my notes real quick, what am I going to have to know to be able to find these values?
Which one you want to use?
Well, but no matter which combination I've used, I'm basically going to have to know sine of u, cosine of u, and tangent of u, yes? So we're going to have to know sine, cosine, and tangent. Now, what did they give me?
Sine is 4/5.
They gave me sine is 4/5.
And cosine is greater than or less than 0.
And cosine is less than 0. Okay. How can this help us? If I need to, before I even get started, I need to know sine, cosine, and tangent.
Could you plug the 4/5 into sine? If you sine of 2 times 4/5.
No. No, we have to use our identity. Okay, we're going to have to use our identity. And our identity for sine of 2 theta, or 2u, is we have to do 2 times sine u times cosine u. Well, 2 is 2. Sine u, we're already told, 4/5. But we have to know cosine u to be able to use that identity. How can I find cosine? So before we start using our identities, this is a go back to chapter 4 type problem.
4? Oh, wait, what?
Now, this is before we did the theorems.
Oh my gosh.
What do we know about sine?
Sine is.
Think SOHCAHTOA.
Oh, a triangle.
Oh, opposite.
Are we doing a triangle?
Mm-hmm. Okay. Sine is opposite of hypotenuse. Now, this is not the bad part. This is not bad, I promise. Okay, I'm getting a death look. Oof, that was rough.
Sure.
Okay, so sine is opposite over hypotenuse, which means opposite over hypotenuse is 4/5. What does cosine mean less than 0, tell me?
It's negative.
Cosine is negative.
So that means that 4/5 is a quadrant 2.
Okay. Quadrant 2, because I need a place to draw this triangle where what is going on? Where cosine is negative. Well, where is cosine negative?
Quadrant 3 and quadrant 4. Wait, no. I lied. Quadrant 2 and 3.
Quadrant 2 and 3. But we know sine is positive, so that puts me in quadrant 2, yes? Are you with me? That was very easy for you at one point. We just have put it in the back of our brain. Is that the problem?
Sure.
Okay. So if we think of drawing this triangle in quadrant 2, okay, the idea that remember your angle of question is at the origin. The right angle is over here. Opposite over hypotenuse. So where's my opposite? Opposite is going to be my y value, my 4. It's going to be going up. Where's my 5? On my hypotenuse. Now, those are both positive values. When you go up, it's positive. Hypotenuse is always positive. Just Pythagorean theorem. Okay. This is just a Pythagorean theorem that this is a y value over here. Whoops. We still have to have an x value over here. So I would say x squared plus 4 squared equals 5 squared. What are you finding? Technically, I'm going to say plus or minus 3. And I know we're going to say, oh, but it's a distance. But you have to consider the quadrant we're in. This adjacent side is going to be what? 3, but it's going to be negative 3 because how do you go left from the origin? You go negative, yes? Okay. Okay, it's rough in here this morning, isn't it? Oof. Okay. This is old news. This is supposed to be old news. Are you with me?
Yeah.
Okay. Now, here's your triangle, folks. I need to know sine, cosine, and tangent. We were already told sine of theta is 4/5. What is cosine?
-3/5.
Because SOHCAHTOA, adjacent over hypotenuse, -3/5. Is it supposed to be negative?
Yes.
Yes, so it makes sense that I made that 3 negative, doesn't it? And what is tangent of theta?
-3/4. Oh, 4. 4/3. That's my bad.
-4/3 if we go opposite over adjacent. Okay. This is your information you have to know to get started.
Started.
Well, we haven't really done the problem at all yet. Okay? Because we were asked to find sine of 2 theta, cosine of 2 theta, and tangent of 2 theta. So let's start by finding sine of 2 theta. What does my identity say about sine of 2 theta?
2 sine u cosine.
So I'm going to translate that to 2 sine theta cosine theta. So I just took the identity from the top of the page, I changed it from u's to thetas. It's the same identity, correct?
Correct.
Okay. What do we know? What can we fill in?
Sine is 4/5 and cosine is -3/5.
So 2 times sine of theta times cosine of theta. 2 times 4/5 times -3/5. You can calculate it. I was just going to brain it, but
Me too.
I mean, what's 2 as a fraction?
2/1.
2/1. So just multiply across. What do we get? Yep. -24 25ths. That's it. So we know that sine of 2 theta is equal to -24 25ths. We're technically a third of the way done with this problem.
Wait. Oh, wait. We have to find the.
Because that was cosine 2 theta, or sine 2 theta.
Why not?
What else were we asked to find?
Cosine.
Okay, so cosine of 2 theta.
Oh no. I'm not leaving. Oh.
And you guys remember, I'm redoing the notes as we go this year. This entire set of notes was on one front side of the page, and there was so not enough room to work. So I gave you lots of room here. But I don't know. I just hadn't redone the notes. So okay, what are your thoughts about cosine of 2 theta? Okay. Cosine squared u minus sine squared u? Now, do we all have to use that one? No. Could someone use 2 cosine squared u minus 1 and someone else use 1 minus 2 sine squared u? Here's the deal. They all come out to give you the same answer. In our case, we have sine and cosine, so does it matter which I use? No, I agree. I would probably use the top one. If I only knew sine or cosine, then I could pick or choose which one of the others to use. But I personally would say cosine squared theta minus sine squared theta. What is cosine? So we're going to do -3/5 quantity squared minus, what is sine?
4/5.
So 4/5 quantity squared. -3/5 quantity squared, what does that become?
-6/5.
Ooh, let's square them, not double them.
Shoot. No, how about that?
Negative times negative is a positive. 3 squared is 9. 5 squared is 25. Minus, what's 4/5 squared? 16 over 25. 9 25ths minus 16 25ths.
7.
-7 25ths. And we have just found
Cosine.
cosine 2 theta. And guess what?
One more.
One more. Find room on your paper somewhere to squeeze one more in. I'll be honest, even because I'm just going across, even I'm starting to run out of room here, but what is my identity for tangent 2 theta?
2 tan over 1 minus tan.
So I'm going to write that with thetas. 2 tangent theta over 1 minus tangent squared theta. If you haven't noticed, I don't throw a big fuss over if you change variables or, you know. You need to try to be consistent. That is a skill to work on. We're also learning, so. Okay, fill in what you know. 2 times, what's tangent theta?
Negative 4/3.
Over 1 minus negative 4/3 squared. Okay, on top, 2 times negative 4/3,
Negative 8/3.
right? It's 2 over 1, and so that is negative 8/3. Denominator, 1 minus, what is negative 4/3 squared?
16/9.
16/9. And you square that negative, so it's still 1 minus. So negative 8/3. What do you know about 1 in terms of ninths?
9 over 9.
9 over 9, yes. So right here, if I go back right here, this 1, can I think of it as 9 over 9? 9 over 9 minus 16 over 9 is going to be negative 7/9. And now what?
Multiply. Or keep it switching to it.
Okay. You're dividing fractions, so we're going to multiply by the reciprocal, or whatever little shortcut you use, right? So I'm going to say we're going to keep the negative 8/3. We're going to change division to multiplication, and we're going to flip. Negative 7/9 becomes negative 9/7. I personally am a cross canceller. So I personally would cancel the 3 and 9. You can multiply and then reduce if you want. One way or another, you should end up with 24/7. And that was tangent of 2 theta. Okay.
It wasn't as bad as I thought it was going to be.
No, these, I like I kind of mentioned when you guys, I was like, what do you think? Well, double angles I like. I really do. And I feel like the double angles definitely pop up a little bit in calc. Okay. So double angles I like. They're kind of fun to use. Questions here? Once we get into it, you're with me? Okay, it was rough there at the beginning, but. Okay. Example 2 when you're ready. Ask us to rewrite cosine to the 4th x in terms of trig functions with no power greater than 1. So we're going to take cosine to the 4th. We want to rewrite it with no power greater than 1. Okay, so that is their, underspeak or whatever for saying use the power reducing identities. Okay, so we're going to take cosine to the 4th x and rewrite it with no power greater than 1. Okay, now, glance up at your power reducing identities. what do we have in the way of power reducing identities?
Cosine squared u.
We have an identity for cosine squared.
You break that up into cosine squared u times cosine squared u and then multiply.
So here's the deal. I don't have a power reducing identity for cosine to the fourth, do I? But I have a power reducing identity for cosine squared. So the way I have it written on my paper is I'm thinking of it as cosine squared x quantity squared. Now, what Katie said, cosine squared x, cosine squared times cosine squared. Is that essentially what this is?
Yes.
Yes. And when I get to a step here later on, guess what I'm going to write it out as? Cosine squared times cosine squared. Okay. Now, what can we do here? Do we know something about cosine squared?
1 plus sine
No. Look at your power reducing identities.
1 plus cosine squared x.
Okay. According to my power reducing identities, cosine squared x is 1 plus cosine 2x over 2. Do I remember it right? And what would that mean? That would mean quantity squared here, yes? Now, and this is where I kind of go to what Katie said, where, okay, cosine squared squared is the same as saying cosine squared times cosine squared, because we need to multiply this out. We need to work with it and see where we're at. So if something is squared, that means you're doing something times itself. So 1 plus cosine 2x over 2 times 1 plus cosine 2x over 2. Okay. How do I multiply this?
Distribute.
Okay. The top part is a distributor, or a FOIL. On top, are you ready? 1 times 1 is 1. Now we're going to look at the outsides. 1 times cosine 2x is cosine 2x. Can I hold on to that one for a moment? Because then what happens with my insides?
1 cosine squared x. We write it as 2 cosine squared.
Not squared though.
Oh,
2x.
Yeah.
Okay, so here my insides are cosine 2x times 1, which is cosine 2x. So I have 1 cosine 2x plus 1 cosine 2x, which is 1 plus 1 is 2 cosine 2x. That's your outside and insides. And then last, cosine 2x times cosine 2x. What happens when you do cosine times cosine?
cosine squared x.
So this is going to be cosine squared of
4.
2x. Now you just keep the variable piece the same. So plus cosine squared 2x. All over 4, because 2 times 2 is 4. Okay. Now, before we continue to we're going to have to do some cleanup. We also need to pause and think about what it was asking us. Rewrite cosine to the fourth x in terms of trig functions with no power greater than 1. What do we have going on here?
Cosine squared x.
Do I still have a power greater than 1? Now I've reduced it, haven't I? I went from having a cosine to the fourth to now I'm down to a cosine squared. So we're making progress, but we're not done.
You rewrite it as cosine 2x times cosine 2x.
Well, that's still a cosine squared though.
Oh, yeah.
Okay?
We use the function again.
We're going to use the power reducing identity again. Okay? Now, with that in mind, the power reducing identity is a fraction, yes? And this is the numerator fraction. So short of putting a fraction within a fraction, I'm going to kind of clean this up a little bit. Or maybe clean up is not the right word. But I'm going to rewrite it in that if we take this and break this into our pieces, what does this 4 in the denominator go with? It goes with each term, yes? When you have one denominator, it goes with each term in the numerator. So for instance, we have a 1 over 4. Okay, are you with me there? Plus, now in the middle we have 2 cosine 2x divided by 4. Well, if you put that out front with the 2, I'm going to write it as 2/4 cosine 2x. Do you see that? I took this middle term of 2 cosine 2x. It's divided by 4, so that's just taking your coefficient of 2 and dividing by 4. You could also write that 2/4 as 1/2, and I will at some point. But right now, if I write it as 2/4, I feel like it's easier for you guys to see. It's not just what magic just happened. Plus, now, when we divide this next piece by 4, what coefficient is out front? It's just a 1. So that's going to be 1/4. And then, you want me to replace or you want me to do that in the next step? How confident are we feeling? I usually replace it here. Are you guys ready to be daring and replace it here? Cosine squared 2x has an identity, yes? Now, there is a slight catch as we go through and do this, but we're going to take cosine 2x and replace it with, what's the identity say? 1 plus cosine, we're going to come back and talk about 2x divided by 2. I'm going to fill that blank in here in a moment. Because here's the catch. When you look at the original identity, okay, I'm going to go back to the original identity for a moment. Where is it? Right here. The original identity is saying, okay, if your original piece is a u, then when you use this identity, this becomes a 2 times whatever u is. Okay? Are you with me there? Now, as we are using this, this right here, 2x, that is in the place of u. Okay? 2x, because it's cosine squared u, according to the original identity up top, right? So that 2x is in the place of u. When we get down here, it's supposed to say 2u. Okay? So if this is supposed to say 2u, what are we doing?
4x?
It's going to be 4x. Yeah, because it's going to be 2 times 2x, which is indeed 4x. Okay, and I will clean it up to be 4x next time through, because we have cleanup to do at this point. Okay, so that's one of the tricky parts you have to watch when we have to use the identity a second time. When it says 2u, it's saying 2 times whatever's in there. 2x was in there, 2 times 2x is 4x. Okay. Ready to do some cleanup here? My first 2 terms are pretty well cleaned up for the moment, right? 1/4 was 1/4. 2/4 cosine 2x, I can, instead of saying 2/4, I can write it as 1/2 cosine 2x. Now, we have a 1/4 here. And then if we're going to make this in the form like everything else, we need to take this fraction and do what we did earlier. Take this fraction Instead of having one big fraction, we're going to split it into two terms. My 2 is the denominator in both terms, yes? So that means the first term within my parentheses is going to be 1 over 2, or in other words, 1/2, plus, when I divide this cosine by 2, well, what's the invisible number out in front of cosine? 1. So this is a 1/2 cosine of 4x. Now, okay, what can I do with these parentheses? Can we distribute the 1/4? Okay. So let's see. I'm still carrying down 1/4 plus 1/2 cosine 2x out front, plus 1/4 times 1/2 is 1/8, plus 1/4 times 1/2 cosine 4x. 1/4 times 1/2 is 1/8 cosine 4x. Okay. We're almost there. Do you see a step we can do? Add like terms. What do I have in the way of like terms? I have a plain old fraction of 1/4, a plain old fraction of 1/8. 1/4 plus 1/8 is 3/8. Yes? Are you guys with her? Because what did she change 1/4 to, we're going to assume?
2/8.
That is 2/8, right? Sorry, I just kind of wrote over myself there. But so 2/8 plus 1/8 is 3/8, plus 1/2 cosine 2x plus 1/8 cosine 4x.
Add
Are you talking about cosine 2x and cosine 4x?
Yeah. So like if you got the 1/8, this would be.
Cosine 2x and cosine 4x themselves are not like terms. In order to add cosines, they'd have to be the same variable piece. So if you're trying to add a cosine 2x and a cosine 2x, we could talk.
So all done?
But we can't. So one option of an answer is this right here. I am going to give you a second option because of how something goes down in homework, okay? But this is simplified, folks. Now, the other option that you will see, I think they have a proof that you have to do, if I recall. Okay, now, the thing is with the proof, we're basically just doing a proof if we knew the answer. Okay? With that in mind, I believe, if I recall, they pull the fraction out. Now, if we could add all these, what would be the common denominator with the fraction? An 8. So if I rewrite this for visual purpose, 3/8, 1/2 is 4/8 cosine 2x plus 1/8 cosine 4x. A skill that you see is to pull out just the denominator so that there's no fraction there. Okay, if I think GCF, I don't know if GCF's the right word, but think common factor, there's a denominator of 8, yes? If I pull an 8 out front, that means I'm pulling out a 1/8 out front. So basically, I'm just pulling that denominator of 8 out. Which means, if I take 3/8 and I factor out 1/8, what am I left with? The 3 on top. Plus, if it was 4/8 cosine 2x and I factor out the 1/8, I'm left with the 4, so 4 cosine 2x. Plus 1/8 cosine 4x, if I factor out 1/8, I'm left with cosine 4x. This is another equivalent way to write the answer. Now, I can't say that I looked at homework this morning or anything to remember exactly how it goes, but I believe the application of this in homework is they would give you something like prove cosine to the 4th x equals this here. Okay, they would say prove it. Now, in order to prove it, what are you doing? These steps in between. Okay, these will be a little rough. We'll have to talk about them when it comes time, but I want you to give them a try. Okay, now what am I at? Do I have about 5 minutes left?
We really need to know.
Well, okay, so let's take a moment, since we do have 4 minutes, but let's take a moment and look at the start of 3, okay? Because here's the deal. The start of 3 is going to kind of mimic number 1, okay?
It's just a half identity.
Right, so number 3, they give us cosine theta is 7/25. They tell us sine is greater than 0. And they ask us to find sine, cosine, and tangent of theta over 2. So it's like number 1, but instead of using our double angle identities, we're using our half angle identities. Okay? Which means if you go back to number 1, what did we start off doing? Did SOHCAHTOA and we figured out our pieces, yes? In other words, we need to know sine. I think you only need to know sine and cosine for half angle identities. Tangent is never used. But you need to know sine and cosine. So what quadrant is this going to be in?
S.
What did I just do?
That was not right.
Wow.
I was going along with it too.
Don't go along with me on that one. Ooh, that was, okay. Sine greater than 0 says sine is positive. What do we know about cosine? Positive. So what quadrant do we have to be in? We have to be in quadrant 1. Oof. Sorry, guys. Okay, so quadrant 1. If I draw a triangle in quadrant 1. Okay. Theta is always at the origin on the x-axis. Right angle is here. What do we know about cosine? This is adjacent over hypotenuse. So adjacent is x. Hypotenuse is 25. And it makes sense that they're both positive. What about opposite?
That's going to be a big number. It'll probably go down to a smaller number. It'll be no. You did that in your head?
I know my squares.
You're a smart cookie.
Yeah. Nope.
I don't know.
I've done this problem before, but I know my squares. Okay, so 625 is 25 squared. 625 minus 49 is 576. Hey, guess what? 576 is a perfect square and is 24. So tomorrow, let's see, we need to know sine theta and cosine theta. Cosine theta was given as 7/25. What's sine theta going to be? 24/25?
I gotta
Okay.
give you all the variations.
Okay, well, you succeeded. Okay, with that in mind, tomorrow we will start off using our identities. Okay? And we'll talk about it. And it really just comes down to plug them in. The simplifying is the key. Okay?